So this is the topic that, okay, excuse me. This is the topic we're saying the shifting of our theory and technologies is forming data-oriented or data training-based learning to knowledge-based or knowledge acquisition for machine learning. So this is a fundamental shift of regime and theories and practice in our areas, because some of the current technologies actually cannot meet the needs for the future of machine learning. So let's look at, okay. So this is the structure for this discussion. So first we're going to present the basic studies about machine learning. And so this is to say, so we are going to compare two of the studies from pre-trained and pre-programmed learning. So first part, we're going to compare the current technologies and traditional technologies and see what is the differences for machine learning. And in the third section, we're going to discuss the cognitive knowledge-based machine learning, and towards something we call it autonomous AI systems, double AI. And then we're going to discuss the underpinning theories. It is a set of mathematical means that enable the future technology for autonomous machine learning. We call it the intelligent mathematics. You'll say the ideas here for basic research, it says we're not only focus the technology, because we need to understand the underpinning theories that are driving the things towards the future technologies of machine learning. So this is the structures, okay? Okay, so this is the review about current approaches to machine learning. So the major things we need to know is the structure of intelligence science. We say intelligence actually is, you see that layered hierarchical structures. From the bottom level is reflexive intelligence in our world. So that's something we as humans share with machines and with animals. But in intelligence science, we get things developed fast. From the bottom layer to the imperative layer, it is program-based. Well, this is the traditional computing technology towards AI, towards machine intelligence. Then we have the adaptive level in third, in the right circle. And beyond that is autonomous and cognitive levels. The cognitive level of intelligence is human level intelligence. So our machines actually are still at the lower level. AI trained machine intelligence actually is the bottom level, reflexive. Okay, and the computing base is in the blue level, second level. It is programmed. And then we say in the last 6 years, we are bounded by the red circle. That's adaptive. Then something would be flexible, but it is not matured enough. And then we try to move forward the intelligent technologies to something beyond the adaptive level. So if you compare the current AI technologies and the computational intelligent technologies, we say it is not necessarily say at this moment AI is becoming greater in intelligence science beyond computational intelligence. And actually, you see the programmed intelligence in the very beginning, in the last 50 years, actually have developed good things. And because the level of intelligent power here is higher, because the first part of AI actually is pre-trained. The pre-trained technology is based on data, and actually it is not enough for real-time decision-making. For very complicated decision-making, we can use the data-trained technologies. We will explain why data-trained technology have so many constraints, because human intelligence is built in a number of levels. We will discuss the details. And then actually, human intelligence, we would call it the natural intelligence. The natural intelligence actually is the number of higher layers because we have the real-time decision-making capability. We have many of the things we are doing internal reasoning. It is autonomous. We don't need to fetch a large set of data. We have internal rules we learned, we built. And we have generic ways for causality reasoning. So all this is not possible for the computation technology or AI technology. So this is the current understanding about the structures, the constraints in intelligent science. So based on that, we say we have a picture to say, okay, in human reasoning and natural intelligence, actually we have 4 levels from bottom up. You see, in our brain, we have 4 kinds of entities from data, information, knowledge to intelligence. And intelligence is not generated from the air, directly from data. And you see, data should be aggregated to information and then to knowledge. And after that, we reach the level of intelligence. Or in other words, we can't jump. We can directly say we collect enough data, and then we can create the best intelligence in the world that would be stronger than human brain. Actually, we can't, because the data in many of the time is infinitive. For example, 1 divided by 0, they created the infinitive space of data. But many of the data is useless. Okay, we can't directly get aggregated from the bottom level to intelligent level. And also, you see, we found in mathematical studies, we found the basic structures of alpha I, we call it abstract intelligence, is aggregated in its levels. And you see the unit of knowledge actually is not discrete data. It is a beer. This is the findings in 2018. It says, what is our knowledge? Our knowledge is the basic unit of our knowledge is a beer, is a binary relation. That means anything we created in our brain, the neural networks, if there is a connection, that's a basic unit of beer to represent our knowledge. It is much, much greater than the level of data, because data is a basic, measurement of the physical unit. And then we have information is a bit, the Shannon to us. But the finding here says knowledge is a beer, is a binary relation. And then we have intelligence, and it is a BIP, it is a binary process or binary function. So this is all the things we understand so far about how the brain process things from bottom up. And it is, you see the intelligence level is much higher than the things of data. We can't directly move from data to intelligence. This is the basic findings. And so based on that, this is my background. I'm working at University of Calgary, but I was visiting professors on sabbatical at a couple of top 10 universities, and also give talks in several of these universities. So based on that involved me into transdisciplinary research that is not only look at the current practice of AI. We are doing the basic studies about the foundations of intelligent science, and also the relationship between AI and brain science. So all these multidisciplinary studies and understanding helped us to pinpoint what is the problems or fundamental challenges here, what is the constraints, and what would be the future for the development. So let's look at the second part is machine learning. I'm sorry. Okay, we say to discuss machine learning, we have so many great developments. But fundamentally, we need to think And in order to develop the future technologies or some basic breakthroughs, we need to discuss, we need to think in other ways is what can AI do? That's a way to think what is the things that was missing. And this is the first example of what can AI do. For example, the first photo, the first photo in the up part is a group photo, and how the best trained AI in the world from Google or other companies, how they do, what is their performance for this photo? Actually, they always make three of the blue circles. The three faces could not be recognized by any best trained neural networks. And makes things worse, if you feed in a photo in the upside down way, what would happen? And all the system will tell you there is no facial information there. So this is the current AI. Why? Because they trained all the photos in a perfect way. That's the training process. So once you fit the photos in the upside down way, and nothing would happen. Okay, so there is no person there. Actually, there are, and also why those three persons are missing by all the systems? Because you see these three persons actually their facial information was quite good, but somehow their eyes was not show clearly. Their eyes was closed during that moment of shooting, the photo taking. So that's what happens. So you see, this is actually a fundamental constraint to our current technology of AI. Although we would consider our AI technology is so smart nowadays, actually these are fundamental drawbacks of our system. And then we say, by understanding that, we can improve the situation. We really can, our system can really autonomously identify if a photo is not in the right position. If somebody's eyes was closed, could we recognize that kind of facial information as well? You see, anything, if you identify the fundamental problem, you can solve it. So I will discuss a little bit about that, but here is the framework of human machine learning. We see machine learning is not only focused on image recognition or object identification and classification with pattern recognition. This is not only the need, and actually we have the right part. This is our wish. We need really in everyday life and research to enable the machines to learn our knowledge. Human knowledge should be eventually understandable and manipulatable by the machines in the future. So that means the machine should be able to capture the concept of our knowledge, our expressions. Eventually, they build a refreshed knowledge base based on their moment of learning. Another thing we see in the future we need is intelligent generation. We want the machines eventually able to generate intelligence based on the knowledge, based on other part of capabilities that would help us to solve some kind of hard problems and help us to do reasoning to find new things. That's the major things, human learning. The machine should be able to do this in the future. Otherwise, it is still data-driven technologies. It is not that powerful. And so this leads to the comparison about how humans do in our life for learning. Actually, learning in human brains, you see, we model human brains at 5 levels, from the sensation levels to memory, to perception, to action, this metacognitive processes, to the higher levels. So there are 5 levels of capabilities in our brain, or in our capability. And the lower 4 levels, we call it the unconscious, sometimes we call it subconscious levels. The top 3 levels are conscious processes. Well, in other words, you compare computer science, you would consider the lower 4 levels is something we call the human operating system. This is ready once a new baby is born. But the higher three levels is our apps, human apps. It's built on the operating system of the brain, but they are doing reasoning, learning, and problem solving at the three higher layers. So you say learning actually is only one of the higher layer capability in our everyday life. So in other words, machine learning, even if it is quite mature, it only solves part of our problem. Actually, we have so many other things for information, knowledge, comprehension, problem solving, decision making, creativity, and planning, planning, and you see all these things are still empty, or the machine AI can do for almost all the high level of things except database learning and pattern recognition. All the rest can be done at this moment by AI. So this is a challenge toward our AI technology series, and also this is a challenge to understand how the brain works there for all the aspects. You see, all the higher level of human intelligence actually is driven by the lower ones layer by layer. For example, deduction, induction is a fundamental reasoning power of human, and we have abstraction and many other things. And no matter to say the lower level things, the machine actually at this moment is processing something in AI actually is very low level things. It haven't reached the high level reasoning power, autonomous intelligence. Okay, so based on that, we say actually the finding is we really can't, just escape from the bottom layer of data immediately to intelligence, because there are several other layers we have to be implemented. Otherwise, we can't jump. For example, if you just base the big data-driven technologies, the machine reasoning in AI will suggest us why the sun will rise every day except today. Okay, but because the the roosters is singing in the morning, that will cause the sun rising. So actually, this kind of database reasoning actually is or is not right, but that gives us a wrong missing the wrong false causality, because that's really there is a relation, but they are not a causal relation. That means if you stop all the roosters singing, the sun is still rising. So they are necessarily they are kind of reasoning, but they are necessarily or efficient. And many other things that the machine learning based on data can reason in the wrong way and got a falsity in all the time. So this is an indicator says intelligence is far away from the understanding about data. It's not say if we collect enough data, we will train the machines or enable the machines to generate great intelligence. It is not necessarily. And human actually, for doing all the things up to intelligence in a clever and smart ways, we do inductive reasoning. We just observe the nature world at the data level for a few times, usually one, two, and jump to I and I plus one, and we know what is that. We don't need the big data. We don't need to do it for infinitive reasoning. Eventually, we see what is something as the rule or something is happening, because the fundamental things here is totally different from the discrete feature of data. And based on that, we say that's the cognitive foundations towards intelligent science, towards our future of autonomous AI systems. So here, then we are going to discuss the cognitive knowledge learning towards the future we call the WAI, the autonomous intelligence, autonomous AI. And we say human knowledge representation in the brain, as we understand that well in neuroscience and brain science, it is the though all those kind of connections. It is supported by neurology that you say our information and knowledge is not stored in a cell as that of computer structures. But we create the synaptic connections to represent our knowledge. So that's why we say the knowledge is a binary relation. It's not a cell element to say where is the knowledge, rather than say the connection by the synaptic structures becomes our knowledge. So in the abstract model, we use the word model to say there's a set of objects. Between objects, there's a set of relationship. And this is called the word model. It says what is our knowledge, internal representations, what is their meanings, and how you manipulate these. This is no longer data. So data-based series can't process this kind of things in our brain. And also, that's lead to one of the discoveries says, what is the capacity of our brain, of generic human brain? How much we may remember, how much we may learn in our life. And actually, this is a model based on understanding says, okay, the capacity of our knowledge base and our memory becomes a combination of the base of how many neurons in our brain. We say it is about 100 billion of cells, of the cells. And then this is the connections, average connections in between all the neurons. The average is 1,000. It could be more, could be less, but the average is 1,000. So then the things becomes a mathematical model is a general combination model based on the base and the max average connections. But somehow this becomes a hard problem because the base and the connections is too large. And no ordinary computer can solve this mathematical model, although this is it's a well-known combination model. And then we found the algorithm to simulate, to reduce complexity of the computing in this way. And then that lead to the solutions of what we found here. It says human capacity average is the power of 10 to the power of, it's 10 to the power of 8,400, something like that. Also observe, the unit is now bit. It's not say how many cells you can put the information there. It says how much the connections you can create. That's just like our networking in conference. We need to link people together. If you think these individual people in our world and all the things combined is our relationship networks for research, for any other opinions. So this is basic understanding. And there was a story actually, this is created in 2003, almost over 20 years ago. Actually, it was in a conference in France. In northern France, we had a conference. Actually, there was 2 keynote speakers. One is from the chief engineer of IBM France in the conference, and another one is me. And somehow mine was the first. And then in the morning, second day, the chief engineer told me he could not sleep. I asked why. He said, you present something like this, and he has to change his perception. Because in his plan, he wants to report in the next 10 years after this, IBM's chips will be much greater than human memory. And after he realized theoretical studies, he understands there is no way, there is any chance to create any kind of mechanical device, electronic device that would be greater than human memory. You see, what does this mean? This means you put all the hard disk chips in the world together. It is still smaller, much smaller than this. This is almost infinity as a number. So that means no company would do that kind of things. From that on, no company discussing their chip capability would be greater than the brain. And that seems because theoretical studies can provide us evidence or principles to say what would happen, what would not happen. Okay, based on that, we say our mathematical model in the basic studies towards EACs, our unit of knowledge is concept. Whatever language you're using, or multiple, bilingual, or multilingual, and the basic unit of knowledge is a concept. And any concept may be modeled as a 5 tuple. There are 5 dimensions, a set of attributes that the individual or sub-concept of the main concept. Then there is a set of objects, that's the denotations, what kind of things may be denoted. This is the attributes, what kind of basic attributes constrains each of the denotation. And then there are a set of internal I/O relations. So that becomes, so this is a basic unit of our knowledge representation in the brain. Or in mathematics, we call it concept algebra that models our knowledge in its basic structures. Then any other things is a combination of that. So this is basic understanding what is the mathematical models of knowledge based on the understanding in neuroscience, brain science. And then a piece of knowledge actually eventually becomes a concept. That's a function of mapping the information you collected, acquired to a concept. The concept is a learning result for a small piece, unit of knowledge. And also observe the unit of knowledge is beer, is not bit. Okay, this is not data, it is a relationship there. And based on that, our entire knowledge, our whole knowledge in knowledge base is the beers connect together. So that's a Cartesian product, a set of concepts in our brain mapped to another side of the concept existing there. And that's a relational function that to generate this mapping. That eventually is our whole knowledge in the brain based on each of the concepts. So all the concepts interconnected, or many of the concepts interconnect together, that becomes our whole knowledge. So based on that, we say we can manipulate this kind of understandings in a mathematical structure called concept algebra. So the concept algebra provides a set of relational operations and reproductive or genetic operations and composition operations to build a higher level knowledge in a hierarchy. So there are only dozens of operators, just like arithmetic, we only have 4 basic operations. In concept algebra, we only have dozens of those kind of operations. Machine can run these individual algorithms to implement each of the operations. Then the machine can reason, can learn our knowledge, can build their own knowledge base autonomously based on these mathematical structures. So this is the illustration says the machines may learn something, say, first learn something as a pen based on the word structures, a set of attributes, a set of objects, and their relationship. And then the machine may learn something, say, as a pencil. This is a pen, and the machine can learn pencil in other way. It shares many of the same attributes, but something would be different. And eventually the machine can reason and say, what you mean as human? What do you mean as human as a stationary? And then the machine says, okay, based on the existing knowledge, they may reason, okay, the stationary is a higher level abstract knowledge based on the concept you already know. Okay, I may skip something because time is limited. And so that's our mathematical model of entire knowledge in the brain. And then this may be implemented in machine learning algorithms. So this is the intelligent-based machine learning. The eventual machine may capture our knowledge in a rigorous way and in a fast way. You see, for this kind of things, we call it the knowledge modeling based on technology ontology. And if for human to process, say, the thousands of human basic knowledge in elementary school, the human need several man years, person years to build such kind of quantitative connections in a knowledge base. But our machine actually just need 1 second to build a knowledge base like this. and the knowledge base could be great, much greater than that, but the machine can do it step by step very quickly. That's why we see the future machine learning is actually will surpass, will overperform human, because they learn this, once they learn, they never forget. And all the machines can share this kind of things as learned. Any machine, so say we assign the thousands of millions of machines, each machine learned a piece of human knowledge or a piece of knowledge in different kind of language. Eventually, the things may be merged together as a whole. That's our human knowledge. And that's a kind of fundamental things towards the future AI, because the AI system needs this knowledge to do reasoning. And so let's look at the last part. Just I need 2 minutes for this. So this is talking about all the things you see driving here by rigorous, intelligent mathematics. It is not driven by program or pre-trained neural network. It's driven by intelligent mathematics. This is the same things in calculus. You see many mechanical systems. It's not driven by data or neural network. It's driven by mathematical structure. In AI, that's the same thing. And so you see the discovery is our representation power for human data types. Actually, from no data type to binary to we've stayed a real domain for too long, but now you see that extended to hyperstructures. And we see all the problems that remain as hard problems in AI actually is the problem domain actually is already out of our domain of mathematical capability. So that's where a set of intelligent mathematics had developed. And actually we found for human, actually every day we only process, manipulate 3 kind of problems to be the entities, to have the functions, and to do the functions, to have it in between. And usually we use this the existing mathematical means. This is something new we developed in framework of intelligent mathematics, because all the entities we're dealing with in AI is no longer data object. It is something more complicated. That's why we need a set of mathematics. That's developed in my lab. You see, that enables machine learning our knowledge rather than image or pictures, patterns, in a very fast aggregation to refine their learning. And some results we already show. So that leads, last slide, okay. That leads to the finding says we enable our new AI technology called cognitive robots. The cognitive robots actually eventually can learn things very fast. Compare human learning to animals. We have an advantage to transfer our knowledge from generation to generation by many means, by universities, information systems, books, papers, conferences. But we have weakness. Our weakness is we have to learn things, you see the consequence, learning things individually or redundantly. You see many of ours in the same areas for same degrees, we learn by ourselves. And we can share our knowledge. We can copy our knowledge among us. But the cognitive robots will eventually do this. And all the learning results will be able to copy to among all the computers. Eventually, that's our great assistant. We need that to develop further reasoning. The machine, aspect of machine reasoning may not be able to do it. Okay, so this is this is a talk where involved a number of future challenge and potential technologies.